We will now begin the journal club. Good evening. Let me introduce you our journal club presenter, Junhyung Cho. Junhyung Cho is an undergraduate researcher at the KAIST Quantum Device Lab and has interest in photonic integrated circuits and quantum emitters. Today, he will present us about photonic quantum computing, foundation, and progress. The paper he used are the 2025 Nature paper titled A Manufacturable Platform for Photonic Quantum Computing by the PsiQuantum Team and a specialized article by Dr. Young-Ik Son on measurement-based quantum computing and PIC platforms. Then let's welcome Junyoung Cho to the stage.
Hello everyone. Um, can you hear me well?
Yes, we can hear you well.
Okay, then I'll start. Before I begin, I want to ask if there is anyone who cannot understand Korean, like because I can do it fully English, but I think it is better to add Korean explanation during the slides if you all understand Korean. Yes, I think all of you can understand Korean, so I will proceed as that way. So my name is Junyoung Cho, and I'm doing undergraduate intern at KAIST Quantum Device Lab. And I'm starting my master's degree from next semester. So I'm graduating this semester. So let's get into it. Uh, but before I start, like I can see there are about 20 people, but uh, I don't know if all of you are present right now, but I want to ask Anyway, I want to ask, like, what is your background education? Like, how many of you? Well, I'm asking this because I don't know how deep I should I go into explanation. Like, could you raise your hand with the Zoom raise hand function if your major is physics? Okay, two people said their major is physics. So I guess other people are from various backgrounds. So I will do not so specific explanation about the deep theory, but rather than I will try to leave at least one knowledge to you guys after this presentation. So I think 30-minute presentation is very difficult to convey big knowledge. Like you will not be able to understand photonic quantum computing with only these slides, but I think if you are able to get at least one additional knowledge from this presentation, I think that would be enough for your future studies. So let's talk about why photons first. I think you will all know that there are many types of qubits that enables photonic quantum computing. Again, like I know, I think many of you already know that there are many methods which enable quantum computing. For example, photons, and there's neutral atoms, and there's ion trap method, blah blah, etc. And among those, I think the most probable method is photon for me because of some reasons, and that's why basically I chose to study on the photonics lab rather than other types of qubit realization methods. So if you ask me why photons, I would say photons have various advantages over other types of qubits, but although I cannot explain all the benefits of using photon at computing systems, I think some of the parts are pretty intuitive. For example, think about other devices of quantum computing, such as neutral atom quantum computing. ion trap quantum computing, you set the initial state on those kind of quantum devices, and what happens? Those physical solid qubits has a common disadvantage that those solid materials can interact with environment. Interaction with the environment harm the quality of the qubit, which makes the limitation called the coherence time. I think some of you will be familiar with this term. So long story short again, some of the physical qubits have to face the fact that they are so vulnerable to its environments because the world we are living is noisy environment. It is not like a pure quantum state. So on the other hand, photons, as you know, photons are very individual and they do not interact with each other, then they do not interact with the environment as much as solid materials. Like for example, if you shoot the light into the water or air or whatever, the frequency of light doesn't change. So neither the polarization of the light, like etc. So photon is a very useful carrier of a quantum state, and also it has advantage of traveling. If you think of other materials like neutral atom, trapped ion, if you want to make it entangled with the other photon, which is like 10 meters away or 100 kilometers away, I would say it is almost impossible because how can you move like a single atom 100 meters by any way? But for photons, it's very easy. You just put a optical cable, which is already very common on the marketplace. You just buy it, and literally anyone can send a qubit to like 100 meters, 1 kilometer long distance. So I think those two, what I wrote on the slide, low noise flying qubit, this best describes the nature of photon, which is useful for our specific application. And now we move on to the how, in detail, how we can we utilize photons for as a qubit. As I listed on the slide, there are many possible methods. At the leftmost side, there is a dual rate encoding type. I've explained it as a picture. Oh, dual lane encoding type. So this is very straightforward, intuitive. So you implement these two rows of the photon. So this would be something like optical fiber, as you know, or it could be a very small structure, micrometer size structure paved on the silicon chip. Anyway, you somehow pave two ways of those which light can go. And then if the light travel at the top way, it's 0. And if light travel bottom way is 1. This is, I think, very intuitive even to the people who don't know about photons before. Also, we can use polarization direction. Like there's H polarization, V polarization. It's horizontal and vertical polarization. As Shinyeon explained on the basic seminar before this journal club, the light has a nature of a unique property called polarization. As you all might already know, it could be used to carry out a certain information. And like third example is a bit advanced topic, but when there's a single photon, you can deliberately make the uh, let me explain this. Think about how can I explain this? Like, you know the Heidelberg uncertainty principle, right? So there's a two axis of uncertainty, and as I drawn here, there's a quadrature of uncertainty. And on this space, you can make the light exist on the certain squidge direction. In other words, you can increase the uncertainty on the x-axis, or you can increase the uncertainty of the p-axis. And this continuous, and there could be many different shapes of light in that sense, and those could also act as a qubit. It's a little bit confusing, but also frequently used. Okay, now we took a look at the why we should use photons and how can photons carry the quantum state information. Now we move to how actually photons can do calculations. I think most of you will be always familiar with the concept of computing relying on the gates. It is uh, nothing special. Like if you think of the classical computer, the original data is loaded on the memory, and there's a logical gates. The original data passes the logical gate, and then there's the result. I think you're already familiar with these concepts or logical computing. And also some types of quantum computing utilize these same methods. For example, like neutral atom computing, ion shell computing, those kind of computing is very similar to those methods in the sense that they also use a gate, but not a logic gate. They use quantum gate, but it's same consequential method that we can intuitively get. But for the light, making a gate is very difficult. That's because making a gate, quantum gate, means like, let's think of the basic gate, CNOT gate, which is frequently used in quantum computing. What does CNOT gate do? CNOT gate's role is to make an entanglement between two states. And to do that, platforms like neutral atom, they physically put two qubits together, and using some physical mechanisms, they actually make an integration between two qubits. However, as you know, light and light cannot see each other. So you learned from the high school, the wave superposition rule. You put the photon and another photon, and how, like, there's no way you can make it together. Again, there's no way you can make them, like, make a interaction. So instead of the gate method, we have to utilize another method called measurement-based quantum computation. So gate-based quantum computation and measurement-based quantum computation is both an algorithm can be used to do a general quantum computation, but the gate computation is more familiar to us. And I think measurement-based computation is just not very much familiar to us, but they are basically, they can basically do same things. They're just different algorithms that can do same things. So if you are interested in the details of how the calculation is done on those kind of measurement-based computing method, you can refer some papers that explain it mathematically, and you will get it easy because those mathematics are not super complex. Those are just they are just limited to the basic words of the quantum information theory. So just a brief explanation is measurement-based quantum computation is not making an entangled state once, once, and once, and once, like the gate-based method. You make a full cluster state, which is a lot of qubits which are already entangled. They are prepared from the start. And then And then there is a big entangled space of qubits, like you can think of, there's an array of qubits, and then you consequentially do the measurement. You do measurement and then another measurement and another measurement. So you keep do the measurement. So you might think, oh, this is not a quantum computing method I have thought before, because it seems like just keep doing a measurement. But it somehow is equivalent to applying quantum gates. And I will not go into too details of the mathematical description, but you will be able to find out if you put some effort in it. So this picture is from the Professor Son's article on the Horizon Webgene, which I posted on for your information before the presentation. So from the left side there is a so-called photonic integrated circuit, and there is many elements I haven't explained yet, but I think you'll get to know better after this presentation. Because this is too complex, I prepared a more simple version. The photonic quantum computing can be summarized into these 3 steps. The first step is single photon generation. To do a computing, you need a photon. That's very basic thinking. So, but it shouldn't be any light. For example, you cannot do computing with just LED light or whatever light. You have to make a single photon because you want to focus on the quantum aspect of the light. And to do that, you need a single photon rather than the classical light, which are around us. And to do that, a very difficult techniques are required. Like I've written here, SPDC, SFWM, quantum dot. Those kind of technologies are making use of the unique electro-optic property of material or the some quasi-atom-like property of the materials, but in common, they are utilized to generate a single photon. So after generating a single photon, you do computing by the single photons you have generated. So as I explained on the slides before before one, so there is a method called measurement-based quantum computation. So with the produced photons, you make a big entangled space, which is composed of the photonic clusters. In other words, you make lots of photons that are entangled to each other, and there's some complex stuff being applied to the qubit. I think you don't have to understand them all in this seminar, but just admit that there are some ways of doing it. And then finally, we detect the result. Detection is also very complex because it is not just detecting a classical light. Like detecting a classical light can be also done by photodiode in the electrical circuit, but this is completely different because we have to detect a single photon, and that is a very, very small energy. So we usually use the superconductor to detect the single photon. So these 3 steps, single photon generation, computing, detection, these are a very simplified version of the photonic quantum computing. So for you guys who maybe are more interested in the topic of the middle computing stage, I've prepared some additional supplementary slides for you to study. So as you can see on this paper, this figure, there's an arrow called information flow, right? So as information goes from left to the right, this means that you do measurements. You first measurement this qubit, and then measurement this qubit, and you measurement this qubit, measurement this qubit. But you can see some of the arrows are heading different directions. For example, arrows here are heading directions towards the screen, and this other arrows has different directions, although all they exist on this XY plane. This means that these successive measurements has to be done in a keep changing basis. And that is what we need a classical circuit called feed-forward. Feed-forward is like I think some of you have a noise canceling headphone, right? How noisy canceling headphone work? It gets the information from the outer environment, and then it process the output, and it generates a feedback inside what you hear. It works very similar to the noise canceling headphones. So you first perform the measurements, and then based on the result of the measurement, you perform another measurement, but with a different basis, and you perform measurement. And this looks very complex, but if you do a bunch of measurements like this, after you check the final result, it produces same result as you did the gate computing. So I think that's the idea, only key idea you have to carry from this lecture. And then now I'm going to explain briefly about the silicon photonics. Silicon photonics is very important because it is key of the scalability, not only for photonic quantum computer, but in quantum computing in general. So before these slides, I keep explained about the basic concepts of quantum computing, but it was all the software stack, right? It was not how it is physically implemented. But from this slide, I will more focus on how it is physically implemented. So photonic computer is not just a idea technology. It actually exists in the real life. There is a chip that can do computation, and the technology behind the photonic computation technology is called silicon photonics and photonic integrated circuit. Photonic integrated circuit technology is, although some of you might be not familiar with the term, this is a very mature technology in the electrical engineering field. As an easy explanation, it is same as the electronic circuit, but it is designed to utilize photons instead of the conventional electrons. So I think many of you will know that there are many technologies that are making use of the photons instead of electrons in electrical engineering field, if your major is related to EE or CS. So those kind of technologies, which are used to produce the conventional CMOS semiconductor or silicon photonic devices, those could be adapted to the photonic computing devices. So I explained about photonic quantum computing because that is the key technology that enables the scalability. Like in theory, any quantum computing model can be realized, but if its size is like a baseball field, then it is useless. But because the silicon photonics technology is very mature technology and it already has working factories, on it, working factories and foundries on it, or making use of the photons is much easier than utilizing other platforms. That's also why photonic quantum computing has strengths over other types of quantum computing. Okay, now I have only a few minutes left. So because this is journal club, I will introduce one journal that actually is related to very recent progresses in photonic quantum computing. There are three major companies who are doing photonic quantum computers in the world currently. One is PsiQuantum. This is in Palo Alto, USA. And there's Xanadu. This is in Canada. And there's Quandela, which is in Paris, France. These three companies have their own way of photon generation, their own way of computing, their own way of detection, but the basic structure is same as I explained it in earlier slides. So if you read their papers this after this talk, you will, I think, better understand the contents of those material. So I captured one representative figure on the most recent paper of PsiQuantum Team. So there's from A to K. This is how there this is uh, figures illustrating how they enables the computing inside a single chip, right? So as you can see on the A, B, and C, this all technology is compatible with conventional semiconductor technology. For your better understanding, I've prepared next slide. So this might look too complex, and you might think, how can we even make one of those things? But look at this slide. Uh, the left one is one from the PsiQuantum. The right is I just got a random CMOS technology paper, which is produced in 2000, year of 2000, right? So you can see like most recent semiconductor technology that exists in our world, like Samsung, TSMC, or the world's most leading companies, they are already very, very expert at making those kind of stacked semiconductor devices. So right side, this is a semiconductor device that do an electronic function, and left side, which I mentioned that I got it from the most recent PsiQuantum paper. This look pretty similar, right? This can be actually produced with a similar factory with the right one, but the difference is the left one is only designed for photonic usage other than electronic usage, but they share the same technology at the fundamentals, and that is why photonic computers are very has advantage over other platforms when it comes to the scalability, because it can just free write on the existing technology, I would say. So if you look at the paper, uh, there are still some key bottlenecks we have to overcome, but still it shows a very good performance on the fields such as indistinguishable single photon generation and single photon switching and photon detections, etc. So I would say best improvements on engineering regime is uh keep on the way, and this is quite encouraging because it means that there is no like theoretical limit. Like it's very different. Like if you have something that it is not like there is a difficult task and impossible task, right? But this is a difficult task, but not impossible task because it already moved to the engineering region. It is not on the pure physics department, but most of the bottlenecks have already changed it into the engineering problems, which means it does not require like a new physics rules to realize. Rather than we can just keep work on the more tight efficiency of existing technology to realize the full photonic quantum device. So the time is a bit over, but let me explain my last slide. So this is the vacuum tubes, and this is transistor. Why I put this picture is to do an analogy between classical computer and quantum computer for your better understanding. So think about it. When there was no such thing as computer, what do we need for an ideal bit? This question is asking you like, who in the world first invented the thing that can store a bit? I would say the first industrialization of the bit was the vacuum tube. However, it was very slow, very big, and very hot when working, so need a specific cooling solution, very inefficient. But after the transistor have been invented, as you can refer from the Moore cycle, the development speed was very fast. This means that the key scalability of technology depends on the realizing a single bit that can be used to do a very precise computing. Similarly, an ideal qubit has also requirements to be met, for example, indistinguishability, low loss, and etc. So, as there was an exponential performance growth were present on the classical computers, also for the photonic quantum computers, if a single qubit is perfectly generated, then the whole system performance will grow exponentially, like similar to what it was done like a classical computing. We just need a transistor for the quantum computer. So in summary, I explained why photons in basic concepts of photonic quantum computing, including some difficult concepts of measurement-based quantum computing, and also I added some how it is physically implemented after those all theoretical aspects. So I introduced a real paper that demonstrates the performance of quantum computing with the basic basic knowledge of silicon photonics for your better understanding later. With this background information, I think if you considering you have a ChatGPT and you can see all the papers on the online, I think now you have the ability to figure out with sufficient time what the paper is saying in a fully manner. So this is what I prepared. Thank you for your attention for 35 minutes, and I'm happy to have any questions afterwards. Thank you. 질의응답은 한국어로 좀 진행을 해보겠습니다. 첫 번째 질문 같은 경우, 박찬민님께서 질문 주셨는데, 첫 번째로 광자 기반 양자 컴퓨터에서는 주로 매저먼트 기반 컴퓨테이션 스킴을 쓴다고 했는데, 게이트 오퍼레이션으로 활용하지 않는 이유는 무엇입니까? 물어봐 주셨는데, 굉장히 좋은 질문입니다. 사실 게이트 오퍼레이션이 훨씬 직관적이고, 그게 더 좋은 방법이라면 그걸 안 할 이유가 없겠죠. 그런데, 앞서 그 영어로 말씀드렸는데, 제가 말씀드렸듯이 광자의 경우 게이트를 만들려면은 두 개의 큐비트가 서로 인터랙션을 해야 됩니다. 그래서 중성원자 같은 경우에는 이제 리드버그 아톰 같은 방식을 써가지고 실제로 이렇게 두 큐빗 중성 원자를 가까이 붙여가지고 이렇게 인탱글먼트를 만드는 식의 어떤 게이트를 활용하는데 광자 같은 경우에는 우리가 광자 두 개를 뭐 갖다 붙여놓고 뭐 어떻게 뭐 이렇게 돌리고 붙여놓고 한다고 해도 광자 두 개 사이에 인터랙션을 만들 수 있는 방법이 사실상 직접적으로는 없어요. 그래서 게이트 기반 방식은 계속 중간중간 인테그먼트를 만들어야 되는데 광자 기준에서는 그게 쉽지 않은 대신에 광자는 이제 초기에 대신에 이제 컴퓨팅을 하기 이전에 많은 수의 큐비트를 준비하는 데 있어서는 중성원자보다 오히려 이점이 있죠. 왜냐하면은 중성원자 같은 경우 실제로 원자 하나가 필요한 건데 큐비트 하나마다. 근데 광자 같은 경우는 예를 들면 어떤 광자가 나오는 분수 같은 이런 플랫폼 퀀텀단 같은 게 하나가 있다고 하면은 광자는 뭐 계속해서 나오는 거니까요. 이제 네, 그런 점에서 이제 제가 레퍼런스에 올려둔 이제 손영익 교수님 자료가 한글로 좀 설명이 잘 돼 있는데 이 부분에 대해서 네, 광자 같은 경우에는 메저먼트 베이스 스킴이 가장 효율적이고 또 반대로 메저먼트 베이스 스킴을 가장 효율적으로 구현할 수 있는 플랫폼도 광자이기 때문에 광자가 주로 그렇게 활용이 되는 것이고요. 그리고 이 게이트 방식과 메저멘트 방식 외에도 아디아바틱이라는 한 가지 방식이 더 있습니다. 그래서 그거는 이제 퀀텀 어닐링이나 그런 식의 용어들로 표현이 되는데 그것도 혹시 궁금하시면은 찾아보시면 이렇게 좀 종합적으로 정리하실 수 있을 것 같고요. 8페이지의 화살표가 아 그쵸 빛의 진행 방향인데 사실 꼭 이 방향으로 가야 된다가 아니라 그냥 이 파란색 길을 따라서 빛 광자가 갈 수 있다라는 거를 시각적으로 표현을 한 거죠. 네. 빛이 이렇게도 갈 수 있고 이렇게도 갈 수 있고 이렇게 보시면은 이제 여러 가지 컴포넌트가 있잖아요. 이런 컴포넌트 하나하나가 뭔지를 이해하려면은 좀 전자기학적인 지식이 많이 필요하지만 추상적으로 생각했을 때는 우리가 제가 앞서 설명드렸듯이 뭐 인텐글먼트를 만들고 측정을 연속적으로 하기 위한 그런 회로다라고 이해해 주시면 될 것 같습니다. 무빙 레조네이터 부분의 끝에 광원 염도 깊이 화살표 진행할 수 있나요?라고 하시는데 좋은 질문이네요. 네, 전자과 베이스가 조금 있으신 것 같은데 사실 이 그림은 사실 논문에서 가져온 건 아니고 도식에 가깝고요. 사실 여기 봤을 때는 그러니까 사실 이 그림 자체가 뭐 그렇게 큰 의미를 가지려고 가져온 건 아니지만 그래도 이제 의미가 있는 질문인데요. 뭐 이렇게 빛이 가면은 여기 광원이 없더라도 이렇게 인접하게 웨이브 가이드 두 개가 위치해 있는 것만으로 이렇게 커플링된 항이 일반적으로 생기게 되죠. 이 거리가 가깝게 되면은. 그래서 그냥 우리가 되게 제너럴하게 얘기했을 때 이렇게 두 개의 웨이브 가이드가 서로 가까이 붙어 있기만 하더라도 이제 마치 우리가 양자역학에서 배운 라비 오실레이션과 같이 이렇게 그냥 여기로만 빛을 쏴둬도 여기 이렇게 빛이 내려갔다 올라갔다 내려갔다 올라갔다 이렇게 진동하게 되는 현상이 있거든요. 이렇게 두 개의 빛이 지나가는 패스가 있을 때. 그러니까 이 그림에서도 봤을 때 지금 뭐 이 그림이 정확히 어떤 용도를 하는 회로 그림인지 실제로 아니면 그냥 이해하려고 만든 도식인지는 그 원문을 봐야지 알겠지만 일단은 뭐 이렇게 이 동그란 부분에 이렇게 빛이 돌고 있다면 일부가 일로 이렇게 세워서 나가는 것 자체는 자연스러운 현상일 수 있겠죠. 네, 감사합니다.
저도 몇 가지 궁금한 게 하나 있는데 음성으로 질문
네,
드려도 될까요?
네네네.
네, 안녕하세요. 저는 디지스트에서 광자 관련 연구하고 있는 양동재라고 하고 여쭤보고 싶은 게 지금 아까 전 페이지인가 보면은 그러니까 퀀텀 메모리가 무조건 그 전 페이지인가?
네네네.
네.
네, 여기죠.
네네. 여기에서 보면은 양자 메모리에서 측정 큐비트랑 연산 큐비트가 따로 브랜치가 따지면서
네.
제가 이해하기로는 그러면 포토닉스 퀀텀 컴퓨팅에는 퀀텀 메모리가 무조건적으로 이게 디벨롭이 돼야지 같이 성장하는 하나의 플랫폼인지가 궁금하고, 두
네.
번째는 그래야 하는 이유가 그 아무래도 포토닉 자체의 광원 자체를 늘리는 건 되게 쉬운 일이나 그 광원 자체가 늘어가는 만큼 데이터를 저장해야 되는 게 클래시컬 컴퓨터와 다르게 익스포넨셜리하게 올라가니까 그거를 감당하기 위해서 양자 메모리가 필요한 게 맞는지 요 두 개가 조금 궁금하거든요.
아, 네. 일단은 굉장히 좋은 질문이고, 혹시 학과가 어떻게 되시나요?
전
질문 좀.
전전 ECS에서 하고 있습니다.
아, 네. 그러면은, 저도 사실, 전자과 전공을 해서, 이게 물리학적인 베이스보다는 그냥 전반적인, 그냥 웨이브 가이드 이론에 좀 더 익숙한데요. 그래서, 그래서 전공을 여쭤본 거는 이제 답변할 때 용이하기 위한 거고, 그래서 굉장히 좋은 질문입니다. 그래서 먼저 첫 번째 질문부터 답변을 드리자면, 이 그림상에서 지금 양자 메모리가 있는데, 그러면은 포토닉 QC 구현에는 무조건 양자 메모리가 필요한 거냐라고 말씀을 해주셨거든요. 근데 이 질문에 대한 답을 드리자면, 양자 메모리라는 것 자체가 되게 지금 폭넓은 용어다라는 걸 먼저 말씀드려야 될 것 같아요. 그러니까, 왜냐하면 사실 우리가 클래시컬 메모리는 굉장히 정형화된 틀이 있잖아요. 하드디스크가 있고, 뭐 USB가 있고, SSD가 있고. 근데 퀀텀 메모리라는 거는 사실 명확한 그런 확립된 게 없잖아요. 애초에 플랫폼 자체도 다양하고. 그래서 뭐 다이아몬드에 있는 어떤 점결함에 있는 스핀 상태가 양자 메모리가 될 수도 있고, 아니면 그냥 어떤 실제로 많이 쓰는 방식인데, 이렇게 파이버를 뭐 여러 바퀴 감아가지고, 뭐 광자 쪽 연구하시면은 많이 익숙하시겠지만, 파이버를 여러 바퀴 감아가지고 그냥 빛이 그냥 채공 시간을 오래 하게 있게 하는 것만으로도 양자 메모리라고 하기도 하고요. 그런데 이제 이 지점에서 양자 메모리가 왜 필요하냐면요. 이 앞서 말씀드렸듯이 포토닉 퀀텀 컴퓨터가 이제 게이트 기반 연산과 동일한 작용을 하는데, 대신에 원리가 조금 다르다고 말씀을 드렸잖아요. 이 메저먼트 베이스드 퀀텀 컴퓨팅은 이렇게, 이렇게 좌에서 이 그림상에서 봤대 지금 좌에서 오러가면서 계속 이렇게 연산을 연산 이렇게 진행을 하면서 그 과정이 이제 결과적으로 게이트를 가한 것과 이코밸런트한 역할을 하는 건데, 이제 그러한 연산들을 이제 연속적으로 할 때 중요한 점이, 한 번 연산을 하고 나면 그 연산의 결과에 따라서 그 다음 연산의, 연산이 아니라 측정이죠. 그러니까 측정이 연산인 거니까 측정을 한 번 하고 나면 그 다음 측정을 어떤 베이시스로 할지를 결정을 해야 됩니다. 그러니까 매 측정마다 베이시스를 다르게 해야 돼요. 그래서 한 번 측정을 하고 나면은 이 측정 정보를 기존 아날 우리가 그냥 그 전자과에서 쓰는 일반적인 회로로 보내가지고, 거기서 이제 다음 베이시스를 어떻게 하면 될지를 계산을 해가지고 그거를 받아와서 다음 측정을 하고, 그다음 다시 이거를 클래시컬 컴퓨터로 보내서 받아와서 계산하고, 이 과정이 끊임없이 반복인 거거든요. 그래서 포토닉 퀀텀 컴퓨터는 그 완전히 포토닉 그 퀀텀 파트만 존재하지가 않고, 그 클래시컬 파트랑 퀀텀 파트가 이렇게 같이 들어가 있는 형태의 컴퓨팅이에요, 기본적으로. 그래서 근데 이제 제가 시간 관계상, 그래서 그 기저를 바꿔가면서 측정하는 게 왜 수학적으로 게이트를 가한 것과 이코밸런트한지까지 설명을 드리기는 좀 어렵고, 대신에 이제 그 이렇게 연속적으로 측정을 계속 하는데 그 기저를 중간중간 바꿔줘야 되고, 기저를 바꾸는 과정은 클래시컬 컴퓨터의 도움을 받아야 된다. 여기까지 그냥 포스툴레이션으로 받아들이신다면, 그 고전 회로에서 기저를 계산해서 갖고 오는 시간이 있어야 될 거 아니에요. 내가 지금 현 상태가 있고, 그 현 상태로부터 다음 측정할 기저를 계산해서 받아오는 그 클래시컬 컴퓨터에 갔다 오는 시간이 필요한데, 그 시간 동안 그 큐비트가 유지가 되기 위한, 그러니까 유지가 어쨌든 돼야 되잖아요, 그 시간 동안. 그래서 양자 메모리라는 게 필요한 거고요. 근데 그게 사실 쉽지가 않죠. 왜냐면 빛 같은 경우에는 다른 중성원자나 이온 트랩이나 어떤 이런 것들과는 달리, 뭐 메모리 뭐 다른 것과 상호작용하지 않는다는 게 우리 장점이자 단점일 수도 있는 게, 빛은 그냥 쏘면 날아가 버리잖아요. 이거를 우리가 한 군데에 잡아둬야지 메모리라고 할 수가 있는데, 한 군데 이렇게 잡아줘가지고 측정을 막 계속 해야 되잖아요. 그 뒤에 메저먼트 베이스 퀀텀 컴퓨터 보면 제가 앞서 설명한 내용에 따르면은. 근데 빛이 이렇게 직진을 계속 하는데 어떻게 측정을 계속 할 수가 있냐? 그거를 해결하기 위해서 필요한 어떤 추상적인 개념이 여기 양자 메모리라는 개념인 거고요. 회사마다 이거를 구현하는 방법은 다 다른데 이제 그 아까 세 회사가 있는데 그 중에 한 회사는 이제 그냥 아까 말씀드렸듯이 그냥 그 옵티컬 파이버를 이렇게 계속 감아가지고 그냥 진짜 이렇게 무식하다면 무식하게 해결하는 방식도 있고요. 또 그 이 칩 안에다가 이렇게 막 그 미로처럼 되게 막 복잡하게 빛이 가는 길을 파요. 그러면 이제 빛이 이렇게 미로니까 빛이 막 이렇게 슉 돌면서 오고 되게 오래 걸리겠죠. 찾는데 그 출구를. 그래서 그런 방식으로 빛을 오랫동안 가둬두는 방식을 쓰기도 합니다. 그래서 그 다음 질문이 광원 자체를 늘리는 것은 쉬운 일인데 그걸 저장하는 게 상대적으로 어려워서 그런 것이냐라고 말씀을 해주셨던 것 같은데 예, 그런 광원 자체를 만드는 것도 사실 그렇게 쉬운 일은 아니지만 네, 쉬운 일은 아니고 거기도 여러 중요한 사항들이 있죠. 근데 이제 양자 메모리가 필요한 거는 방금 제가 말씀드린 그런 것들 때문이고요. 혹시 추가로 질문하신 거 있으시면 답변 드리겠습니다.
저는 보편적으로 되게 잘 이해가 됐습니다. 감사합니다.
네, 감사합니다.
If there are no more questions, we'll wrap up today's journal club here. Please give a round of applause to Junhyung Cho for the great presentation. Thank you all for your time and participation.